On April 17, 2026, engineers at NASA's Jet Propulsion Laboratory transmitted a command toward the most distant machine our species has ever built. The signal traveled at the speed of light, and it still needed 23 hours to arrive, because Voyager 1 is now more than 25 billion kilometers from Earth, moving through interstellar space far beyond the planets of the solar system. The command carried an instruction that nobody on the team wanted to send. Shut down the low-energy charged particles experiment, an instrument that had been measuring the radiation environment around the spacecraft almost without interruption for 49 years. The shutdown sequence itself took 3 hours and 15 minutes to run, and confirmation that it had worked needed another 23 hours to crawl back across the dark. One small detail in the procedure reveals how the engineers actually think about this spacecraft. A tiny motor that spins the instrument's sensor was deliberately left running, drawing just half a watt, so that the experiment could be switched back on if spare power is ever found again. That hope is not sentimental, because this month, in July of 2026, the same team is preparing the riskiest engineering operation in the mission's entire history, a maneuver they call the Big Bang. The problem Voyager 1 faces cannot be repaired, because it is not a malfunction, it is arithmetic. The spacecraft carries 3 radioisotope thermoelectric generators, devices that convert the heat of decaying plutonium-238 into electricity, and radioactive decay follows a schedule that no engineer can renegotiate. Every year, the available power drops by about 4 watts, and as of 2026, the generators produce less than half of what they delivered at launch. During a routine roll maneuver on February 27th of this year, power levels aboard the spacecraft fell unexpectedly, and the team at JPL understood that any further drop could trigger the onboard undervoltage protection system, a piece of fault logic that begins switching off components on its own to protect the vehicle. Recovering from that state, across a 46-hour round-trip communication delay, would take weeks and carry risks of its own. So mission manager Kareem Badarudin and his team chose to act first and retire the instrument on their own terms. A deeper constraint makes every one of these decisions harder than it appears, because the spacecraft cannot simply be powered down to some safe minimum. In the cold beyond the solar system, the hydrazine lines that feed its thrusters will freeze if the vehicle loses too much internal heat, and a frozen fuel line would end the mission as surely as an empty battery. Every remaining watt is therefore balanced between science, communication, and simple warmth, and the order in which the instruments would be sacrificed was negotiated years in advance by the science and engineering teams, written down and agreed upon like a will. Of the 10 instrument sets Voyager 1 carried at launch, 7 have now gone dark. The mission that this arithmetic is slowly closing began with a coincidence of orbital mechanics. In 1965, a young researcher at JPL named Gary Flandreau was studying trajectories to the outer planets when he noticed that in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would drift into an alignment that occurs roughly once every 176 years, an arrangement that would let a single spacecraft use the gravity of each planet as a slingshot toward the next. NASA built 2 probes to catch that window. Voyager 2 launched on August 20th, 1977, and Voyager 1 followed on September 5th on a faster trajectory, overtaking its twin before the year was out. The engineers who assembled them expected a working life of about 5 years, which was enough to reach Jupiter and Saturn with some margin to spare. When Voyager 1 swept past Jupiter in March 1979, it returned images of an atmosphere far more violent than anything the earlier Pioneer probes had recorded. And then it delivered a discovery that no one had planned for. While examining a navigation image, an engineer named Linda Morabito noticed a faint crescent of light rising 300 kilometers off the edge of the moon Io. And that crescent turned out to be a volcanic plume, the first active volcanic eruption humanity had ever observed anywhere beyond Earth. A year and a half later, in November 1980, Voyager 1 reached Saturn and measured the atmosphere of the giant moon Titan, finding a cold nitrogen envelope denser than the air above our own planet and rich in the carbon chemistry that precedes biology. That Titan flyby carried a price that shaped everything which followed, because the trajectory required to skim the moon threw the spacecraft up and out of the plane of the planets, ending its planetary tour after only 2 worlds. Uranus and Neptune were left to Voyager 2, while Voyager 1 was committed forever to a path leading away from everything. That single navigational decision in 1980 is the reason this particular machine, rather than any other, became the most distant object we have ever made. A record it formally claimed on February 17, 1998, when it overtook the older Pioneer 10, and a record it has extended every second since. The long sequence of sacrifices did not begin in 2026, because the pattern was set 36 years ago. On February 14, 1990, engineers commanded the spacecraft to turn back toward the Sun one final time and photograph the worlds it was leaving behind, producing a mosaic of 60 frames that became known as the family portrait of the solar system. In one of those frames, from a distance of 6 billion kilometers, Earth occupies barely a tenth of a single pixel, a point of light so small that Carl Sagan, who had campaigned for the picture, described it as a pale blue dot suspended in a sunbeam. Immediately after those images were transmitted, the cameras were switched off permanently to conserve power, and no one has seen through Voyager's eyes again. Every era of the mission since then has been defined by another deliberate loss, with the ultraviolet spectrometer, the scan platform, and one heater after another falling silent in exchange for a few more years of flight. And the instrument shutdown of this April is simply the latest entry in a ledger that has been kept since 1990. What the mission bought with those sacrifices was a destination no spacecraft had ever reached. On August 25, 2012, the plasma wave instrument led by physicist Don Gurnett registered a sharp rise in the density of electrons surrounding the spacecraft, exactly the signature expected where the thin, hot wind streaming from the sun finally yields to the denser, colder matter that drifts between the stars. Voyager 1 had crossed the heliopause, the outer boundary of the sun's protective bubble, and had become the first human object to sample true interstellar space. The material out there is astonishingly sparse. It is not silent. And in 2021, a Cornell researcher named Stella Koch-Ocker found within Voyager's data a faint, persistent hum, the continuous vibration of interstellar plasma, playing in the background of every measurement like a signal from the galaxy itself. 2 instruments are still listening today, a plasma wave sensor and a magnetometer, and together they continue to map pressure fronts and magnetic structures in a region of the Milky Way that no other machine has ever touched. The data arrives on Earth as a whisper of less than a billionth of a watt, which the 70-meter antennas of the Deep Space Network gather out of the noise every day. It is worth remembering just how early in the journey this still is, because although Voyager 1 left the sun's bubble of solar wind 14 years ago, the sun's gravitational territory extends much further, and at its present speed, the spacecraft would need roughly 30,000 years to pass through the Oort cloud, the shell of distant comets that marks the true outer edge of the solar system. The team that keeps this mission alive has already rehearsed for disaster. On November 14, 2023, the Flight Data System, the computer that packages science and engineering measurements for transmission, abruptly stopped sending intelligible information and began repeating a meaningless pattern of ones and zeros. The carrier signal still arrived, which meant the spacecraft was alive and listening, but for 5 months it could not say anything, and engineers, many of them younger than the hardware they were debugging, worked through documentation written in the 1970s to find the cause. The fault was eventually traced to a single failed memory chip, holding about 3% of the computer's code. And since no part of a machine 24 billion kilometers away can ever be replaced, the team rewrote and relocated that code in sections across the surviving memory, testing each change across a 2-day round trip of radio silence. In April 2024, the first coherent engineering data returned. By June, the science instruments were speaking again, and project manager Suzanne Dodd's team had performed something close to remote surgery on a computer built half a century ago. The Big Bang is the most ambitious version of the strategy the mission has followed for decades, compressed into a single, coordinated sequence. Instead of retiring one device at a time, the team intends to switch off an entire group of powered components at once and bring lower power alternatives online in their place, rebalancing the spacecraft's warmth and electricity in one stroke, which is exactly why the maneuver earned its name. The sequence was tested first on Voyager 2 during May and June of 2026, because the twin carries slightly more power margin and flies 4 billion kilometers closer to home, making it the safer patient. If those tests hold, the same operation will be attempted on Voyager 1 no earlier than this month, and at a distance of 23 light hours, there is no such thing as supervision, because the entire sequence must execute on its own long before anyone on Earth learns whether it worked. The reward justifies the risk, since a successful swap could carry the spacecraft to September 5, 2027, 50 years to the day since it left Florida, and it might even free enough power to restart the low-energy charged particles experiment, which is precisely why that small half-watt motor was left spinning in April. Matt Hill of the Johns Hopkins Applied Physics Laboratory, who leads that instrument, has said openly that his team is holding out hope of switching it back on. There is one more threshold waiting regardless of the outcome, because before this year ends, the one-way travel time of Voyager's radio signal will pass 24 hours, making it the first machine in history to stand a full light day from home. With careful management, NASA's engineers believe the two Voyagers can keep transmitting into the early 2030s, and the Big Bang is the plan intended to get them there. Whenever the final transmission comes, in this decade or the next, the mission will not so much end as change state. Voyager 1 is leaving the solar system at roughly 17 kilometers every second, a speed that carries it about 1.5 million kilometers farther from Earth each day, and no force remains anywhere on its path to slow it down. In about 40,000 years, it will pass within 1.6 light-years of a small red star called Gliese 445, drifting closer to that foreign sun than to our own. Bolted to its side, it carries the Golden Record, a 30-centimeter disc of gold-plated copper assembled by Carl Sagan's committee in 1977, holding greetings in 55 languages, the sounds of surf and thunderstorms and human heartbeats, and 90 minutes of music from across the Earth. In the near-perfect vacuum of interstellar space, there is almost nothing to wear a spacecraft away. No air, no weather, and almost no dust, which means the Voyagers will likely remain intact for hundreds of millions of years, and quite possibly longer than our own planet remains recognizable. The machine was built with roughly the computing power of a modern car key. It weighs less than a small car, and it has outlived most of the people who designed it. Long after its transmitters fall silent, Voyager 1 will continue doing the only thing it has ever truly done, moving outward through the Milky Way with a record of Earth fixed to its frame, traveling deeper into a universe that is mostly empty space, and getting farther from home every single second.